So today we're going to take a look at this hydrostatics problem. So a circular submarine hatch has a diameter of 80 centimeters. It's positioned on the vertical side wall of the submarine and is hinged along its top edge. So we see a picture of that here. Here's a section of the submarine wall. Here's the hatch here. This is a circle, and it's shown in an orthogonal view over here. So the hinge is along the top, and it's 10 meters from the center of this hatch up to the surface of the water. And the sailor is pushing at the bottom of this hatch trying to open it. So that's what we're asked to find here. How hard will the sailor have to push at the bottom of the hatch down here in order to open it? And we're assuming that the pressure on the inside of the submarine here is atmospheric pressure. So to begin a problem like this, we need to realize that we're looking at the static equilibrium of this hatch. So before we start any fluids calculations, we want to look at a free body diagram of the hatch itself. So that's what we're going to do, is we're going to draw a free body diagram. And I'm going to show it in this view here. So we'll just reproduce the hatch here. So that's our hatch. The water is on this side. The inside of the submarine is that side. So the water is pushing this way, and the sailor is pushing there. All right? So now that's our free body diagram. We want to add to it some important things that free body diagrams have to have. First thing I'm going to put on is a coordinate system. So I'm going to put the origin of my coordinate system up here at the hinge, and we'll talk about why when we get a little further into the solution. I'm going to choose my x-coordinate to be pointing into the water, and I'm going to choose a z-coordinate, which I'll show down here, pointing straight down. So the origin of the coordinate system is there, z is down, x is over that way. So realize that the y-coordinate is pointing straight out of the screen. It's a right-handed coordinate system, so y is pointing directly out of the screen. And that'll become important later on. So that's our free body diagram. That's the coordinate system. Now we need to put forces and moments on that free body diagram. Well, the first force that I'll put on there is the force that the sailor is exerting on the bottom. So we're going to call that F, and that, of course, is what we're looking for. And so we're going to assume here, and we'll add this to our assumption list at the end, that the sailor is pushing horizontally. In other words, perpendicular to the gate. If they were pushing slightly up or slightly down, they're going to need to exert a larger force. But we're assuming they're going to push horizontally at that point. So that's the force exerted at the bottom. There's a pin connection up here, of course. The hatch is connected to the submarine through a pin connection, the hinge. So there's certainly going to be a reaction force in that hinge. And so I'm going to call that RH. And realize right now I'm not worried at all about what the direction of that force is. If it turns out we need to figure out the direction of that force, we'll solve for RH and get its sign properly. This arrow is just representing the force acting at the hinge. All right? So that's the force of the sailor pushing and the reaction force in the hinge. Now, notice I'm not going to put any moment due to friction at the hinge, because we're going to be assuming that this is a frictionless hinge. So assuming no friction there, we're going to be solving for this force. Realize if there was a whole bunch of friction there, it would be even harder to open. Turns out this is going to be really hard to open, but if there were friction there, it would be even harder. So we're going to assume that it's a frictionless hinge. And that'll be in our assumption list at the end. So next thing we need to talk about is the effect that the fluids have on that gate. They're certainly exerting forces on the gate and moments around that origin. So because I've put my origin there, I'm going to represent the effect of the fluids on that gate by a force there. And I'll show it a little bit down just so that we can see it easier, but it's acting through the origin. And so that's the force due to the fluids on the gate. And then there's, of course, also a moment around that origin due to the fluids. So we represent that by ms. So a force and a moment are the combined effect of the fluids on that gate. Now notice I'm saying fluids, because in those force and moment, we're going to include both the water pushing from this side and the air pushing from that side. We need to include both of those. We're going to see how that's done when we go through the solution, but realize that those two things, the force and the moment, represent both of those things, combined effect together. So those are all of the forces and moments that we need to include on this free body diagram. So next thing we're going to do is realize that we need to solve for this force. we don't really need to solve for this reaction. So if we take moments around this point, this reaction doesn't contribute to moments around that point. So the only two things that contribute to moments around that point are the force from the sailor pushing and, of course, the moment that the fluids are creating. So our general approach to this problem is going to be to take a sum of moments around the origin, and of course that needs to be equal to 0. So that's our starting point. The sum of moments around the origin has to be equal to 0. And there are two things producing a moment, so we'll represent those by the moment due to the applied force F, so that's a moment created by this, plus the moment due to our fluids, ms, is what we're calling that, all right? So notice I haven't tried to assign any signs to this. These two variables represent the moment. Whether it's positive or negative is going to come out in the math, all right? So two things contributing to the moment. So first of all, let's think about the moment due to the force. So the moment due to that force is going to be equal to this magnitude of the force F multiplied by this distance. And this distance is just the diameter of that hatch. So I just multiply that by d. So there I've got the magnitude of that moment. Now if we remember what our coordinate system looks like, y is pointing straight out of the screen. So certainly this force is producing a moment around this point in the positive y direction, or in the j hat direction. So the direction of this is j hat. So that's our moment due to the fluid. F d times j hat. Now F is what we're looking for, d we know. So all that remains is to find the moment due to the fluids, and we can come back to this sum of moments and solve for this F. So most of our work here is going to be calculating the moment due to the fluids. So we have our basic equation for calculating the moment due to the fluids. So remember, this equation calculates the moment due to a pressure distribution on a surface. So the integral that we're doing here is over some surface, and it's taking moments around the origin. So r is a position vector, n is our normal vector, p is an expression telling us how the pressure varies on that surface, and then dA is an element of area. So that's our basic equation for calculating the moment due to distributed pressure on a surface. Now realize this is a hydrostatics problem, so we're going to be getting this pressure distribution from the basic hydrostatic equation as we go forward here. However, the reason that we're taking this approach, this very generalized approach to finding a moment, is that if we have more complicated situations, like perhaps an airfoil surface, where the pressure distribution is more complicated and comes from some other set of equations, we still use exactly the same approach here. We just put a different pressure distribution in here, and this is how we take that distributed pressure and calculate a moment from it. So I'm doing this in the context of fluid statics as a way to learn how to use this equation for more complicated situations. All right, so let's proceed forward with this problem though. So first thing we want to do is identify our r vector for the coordinate system that we have set up. So realize r is a vector whose root is at the origin and whose tip is at any point on this surface, right? Well, that's just going to be z k hat, because I've aligned my z-axis with the surface, so the distance from the origin to any point on that surface is just z, and it's in the k hat direction, right? Next thing, the unit normal. So remember, the unit normal in this equation is perpendicular to our surface, projecting into the fluid that we are considering. So we're primarily going to consider the water on this side. So our unit normal vector looks like this, perpendicular to the surface, projecting into the fluid. So that unit normal vector in our coordinate system is just I hat, all right? And so r cross n is just z j hat. So we're ready to put z j hat into our integral here when we reassemble it. That's what r cross n is for this particular coordinate system, all right? Now, the next thing we want to do is talk about the pressure distribution. Well, pressure distribution is going to come from the basic hydrostatic equation. So our starting point to get the pressure distribution is our basic hydrostatic equation. So this tells us the pressure gradient for a fluid in a hydrostatic state as a function of the local acceleration due to gravity and any overall acceleration that there is in the problem. Well, realize there is no overall acceleration here. This submarine isn't taken off from a stop or anything like that. So this acceleration is 0 in this case. And that will go in our assumption list when we assemble it at the end. And for our coordinate system, again going back to our free body diagram, realize G is down and that's in the Z direction. So this is G K hat. That's our acceleration due to gravity for the coordinate system that we established. So realize that we only have a K component on the right-hand side equation. Therefore, the only component of the pressure gradient that's not 0 is also the K component. So we can just extract that out. So this tells us dP dz, and that's just the K component of our pressure gradient, has to be equal to rho g. All right? So that's the pressure gradient in this fluid. But of course, we need an expression for pressure, not pressure gradient. So we integrate that, and we integrate this equation. We get P is equal to rho gz plus constant. All right? So notice we've done an indefinite integral there so that we have a constant of integration. And we did an indefinite integral because we need to know pressure at any location z on our free body diagram. We don't just need to know the pressure difference between two specific points, like perhaps we would need in a manometer problem or something like that. So an indefinite integral, so it has a constant of integration in it. So in order to evaluate the constant of integration, we're always going back to our diagram here and asking ourselves, is there one place where we know what the pressure is? And of course, we know that the pressure is atmospheric up at the surface of the water, right? So we can say at Z equal minus H0, I'll talk about what that is in a moment, the pressure is equal to 0. So this H0 is the distance from the origin up to the surface of the water. And realize because my Z is pointing downwards, the Z coordinate of the surface of the water is minus H0. And H0 in this particular problem is 10 meters. So 10 meters is the distance down to the center here. 10 meters minus the radius of this thing. So that'll be 9.6 meters. That's the value of H0 from the information given back on the diagram. So I'm using H0 here just to do this symbolically. So this tells us that C then is equal to rho g H0. And finally, our expression for pressure is rho g H0 plus Z. So that expression tells us the pressure at any location on the hatch. So that's ready to be substituted into here. Now I want to say something important about setting this pressure to 0. So realize setting the pressure to 0 at the surface of the pool essentially means this P is a gauge pressure. So this expression for pressure tells us how much higher the pressure is at any point on this surface, how much higher it is than atmospheric pressure. All right? Well, realize we have atmospheric pressure on this side. So by using a gauge pressure here, setting this to 0, we're basically automatically removing the effect of the atmosphere pushing on the other side. You could think of this pressure as an equation for the pressure difference on the two sides. So we have a very large pressure on this side, but there is still pressure pushing on this side. So the gauge pressure is the difference between those. So this step right here is how we account for the fact there's actually air pushing on the other side. So that's why this MS here, the way we're calculating it, represents both the effect of the water and the effect of the air all together in one integral. All right? So that's an important thing about how we chose this constant of integration. That's the step that automatically accounts for the air on the other side. So now we go on to our dA, the last thing we need to talk about before we can assemble this integral. So here's where we need to remember that this is actually a circle. We're looking at it in section view here, but if we look at it orthogonally to that, from this direction, we see a circle, all right? So dA, the most convenient way to integrate over a circular surface is to use an element of area that looks like r dr d theta. all right? So RD theta. So we'll take a look at what that looks like. So here's the surface that we're integrating over. Center of it is right there. I'm going to define a coordinate theta that is 0 on that horizontal line and is positive going this way. So that's my theta coordinate, all right? And so there's also an R coordinate. So the coordinate of this point, of course, it has a ZY coordinate as well, that point, but it also has an R theta coordinate. We can use R theta coordinates to describe the coordinates of that point. And so because the surface that we're integrating over is a circle, it turns out to be much more convenient to use R theta or polar coordinates in order to do the integration over that circle. And so an element of area in R theta coordinates is R dr d theta. So just take a look at where that R dr d theta comes from. So here I've shown a small segment of that circle. So the angle between these two lines would be d theta. And that means that the arc length out here where I've drawn my element of area is r d theta. And then we multiply it by dr, or the radial dimension of that small element of area. So the r d theta is the arc length, and the dr is the segment in the radial direction. So r dr d theta is the expression for that small element of area. And we'll talk about the limits of integration when we're setting it up, but we're going to go in theta direction from 0 to 2 pi, and in the r direction from 0 out to the radius of the hatch. So we've defined everything in this integral. So I'm going to rewrite this integral now with all of those things substituted in, and then we'll proceed with our solution. So this is the entire integral reassembled. So we have our r cross n here, zj hat. We have our expression for pressure, rho g h naught plus z. And then finally our element of area, r dr d theta. So the last thing that we need to be careful about here before we proceed is to realize we're integrating with respect to r and theta, all right? So our limits of integration on r will be from 0 to the radius of the hatch, which is 40 centimeters. And on theta, it's a full circle, so we're going from 0 to 2 pi. So because we're integrating with respect to r and theta, the only variable we can allow in here is r and theta. And currently we have z in our integral. As we move around on that surface, z is changing. So we need to represent z as a function of r. So if you remember what our circle looked like, center is there, theta is 0, measured like that. That's our theta coordinate. So this point right here also has a z coordinate, right? And our z is 0 there, and positive going down. That's our z. So we need to write z as a function of r and theta. So that equation is going to be z is equal to r, which is the distance from there down to the center, minus r sine theta. And r sine theta will be this vertical distance here. So the z coordinate at that point is r minus r sine theta. So this is the equation that connects z, which occurs in here, to our variables of integration r and theta. So we need to substitute this in for these two z's before we can do the integration. So that's going to look like that. Notice that I've brought out of the integral anything that is constant. So the rho, the g, and the j hat are all constant, so I brought that outside of the integral. So now we have only r and theta as variables inside of that integral. So I'm just going to put parentheses around this h naught plus r. Those are both just constants, so that can be carried forward in the math just together. So the next thing we need to do is multiply out these two terms. And while we're doing that, we need to remember there's an extra r here. So we're going to bring that into the expression as well. So that's the equation all multiplied out. First we'll do the r integral. So next we're going to do the theta integral. So that's the result of the theta integral. Next we substitute in the limits. Finally, we can clean this expression up a little bit. So that's our final expression for the moment produced by the fluids on that surface. So the last thing we need to do is bring that back into our sum of moments. So all we're going to get for our final expression for F is just this quantity moved over to the other side of the equation. So this will become positive and also divided by D, which was the moment arm that the applied force was acting over. So our final expression for this F, after we do that, is just as follows. So the last thing we need to do is substitute in all of the numbers that we have and solve for our final value of F. So the final value we get when we calculate all of that out is 24.9 kilonewtons. So 24.9 kilonewton force would have to be exerted here in order to open this gate. So this is a very, very large force. This is like 5,600 pounds or something. So there's no way a sailor is going to do it, but if they needed to, that's what the force would have to be to open that hatch. So that's our force. So the last thing we need to do is write our concluding statement, and we'll come back and fill out our assumptions list. So that's our concluding statement. Now the assumptions that we made along the way to come up with that number are also important. So if we think back through our solution process, the assumptions that we made, we assumed that this fluid was in a hydrostatic state. So that's how we could use the basic hydrostatic equation. When we integrated it, we assumed rho and g are constant. We also assumed there was atmospheric pressure inside of the submarine. When we did our sum of moments, remember we said this hinge was frictionless. And you also remember that we assumed that the sailor was going to push horizontally. So I believe those were the assumptions that we made along the way to come up with this 24.9 kilonewtons. So those assumptions, remember, are just as important as the number, because that number needs to be viewed or used in light of the assumptions that were made. So I hope you found this video useful, and it helps you to learn how to calculate moments on submerged surfaces in a very general way. Thank you very much for watching, and ask questions or comments below. Thank you.